Okay, so this is the second lecture, and today I want to discuss how to count and how to construct solutions. So remember, we are discussing solutions of polynomial equations with complex coefficient. We have polynomials in n variables. Take some polynomials in n variables and set up a system of polynomial equations. Okay. Then we want to now use our results from first lecture to answer basic questions. So last time we did two versions of Null-Schönjats. Two versions of Hilbert Null-Schönjats. The weak Null-Schönjats. That says the structure of maximal ideals. So every maximal ideal of R is of the form M A, where MA is the maximal ideal generated by x1 minus a1, x2 minus a2, xn minus an for some point A equal to a1, a2, an in Cn. And using this, we showed the consistency criterion that the variety defined by these S polynomials, this is algebraic variety defined by these polynomials, and it is the set of common zeros of these polynomials, all these polynomials. Okay, this is non-empty if and only if the ideal generated by these polynomials is not the whole ring. Okay. So using the structure of maximal ideals, we proved when a system of polynomial equation has a solution. So the ideal generated by those polynomials should not be the whole ring. And then we did the strong Null-Schönjats. Strong Null-Schönjats. The strong Null-Schönjats talks about radical ideals, a one-to-one correspondence between radical ideals and algebraic varieties. So on one hand, we have ideals in our ring in n variables over complex field, and on the other hand, we have the n-dimensional affine space Cn. And here we look at radical ideals. That is, ideals which satisfy the condition that I is equal to its own radical. And algebraic varieties related to with these ideals. Okay, VR. So the correspondence is given by I mapping to Vi, that is this correspondence, okay, in one direction. And in the other direction, suppose I have an algebraic variety in Cn, then I send it to its ideal. The ideal of an algebraic variety is a radical ideal. It consists of all polynomials which vanish at every point of A. And this is a one-to-one correspondence. Yeah, these assignments, I mapping to Vi and W mapping to IW. These are inverse operations. And this is what strong null says. Strong null says that the ideal of variety of an ideal is equal to its radical. This is the strong null-Schunz. Okay. So if I is a radical ideal, then I get back my I, because radical of I is equal to I. Okay. So these two versions of null-Schunz, they are fundamental in answering questions about polynomial equations. So let us look at the second question, that when is Vi finite? We know when it is non-empty. It is non-empty if and only if I is not the whole ring. Next, we ask when is Vi finite? When does a system of polynomial equation have only finitely many solutions? So when is the cardinality of the set of solutions is finite? Okay. So if Vi is finite, and non-empty, if this is finite and non-empty, then Vi is called a zero dimensional algebraic variety, because it is a discrete set. It's a finite set. So it's just a bunch of points, and therefore it makes sense to call such a set as a zero-dimensional algebraic variety. It's an algebraic variety. I'm not going to define dimension in general, but Vi, if it is finite, it is called a zero-dimensional variety, and I is called a zero-dimensional ideal. And such an I is called a zero-dimensional ideal. So we want to understand when an ideal is zero-dimensional or when a algebraic variety is finite or equivalently zero-dimensional. So suppose the set of solutions is finite. So suppose the set of solutions of my given polynomials which generate the ideal I is finite, and I list the solutions. Suppose the solutions are P1, P2, Pm. Okay. So this is contained in the n-dimensional subspace vector space Cn. These are finitely many points. So how do we recognize that Vi is finite? Okay. So if it is finite, then let us look at a point P1. Okay. Let us take the first coordinates of all these points. Okay. Let us look at the first coordinates of all these points. So P1, suppose P1 has coordinates A11, A12, A1n, and P2 has coordinates A21, A22, A2n, and so on. Okay. Now look at the first coordinates. So take the first coordinates, all these first coordinates. Then consider the polynomial x1 minus a11, x1 minus a21, x1 minus am1. This is a polynomial in the variable x1 alone. Yeah. Now this polynomial, when I evaluate at any point in my variety, it gives me 0 by construction. Yeah. Is that clear? This polynomial in one variable vanishes at every point of my algebraic variety Vi. Yeah. So therefore, this fx1 belongs to the ideal of variety of I. Ideal of variety of I consists of all polynomials which vanish at every point. But my Vi is finite, and this f is vanishing at p1, p2, pm. So therefore, this is an ideal of variety of I, but by strong null Sunjats, this is radical of I. So that means there is a power. Let me call this polynomial by f1 x1. Okay, so there is a power of this polynomial which belongs to I for some d1 bigger than equal to 1. And you can then look at the second coordinates and construct a polynomial in x2 whose some power belongs to I, and so on. Yeah. So similarly we can find f2 x2. So f2 x2 is product of x2 minus the second coordinates of all the points. And by same reasoning, this polynomial has some power which belongs to I, and I can find a mth polynomial. I mean, there are n. Yeah. So that some power is in I. So therefore, the ideal was generated by some polynomial which may involve many variables. Yeah, they may involve many variables. But what we have found is if Vi is finite, then ideal I contains pure polynomials. Okay, in one polynomial in x1, another polynomial just in x2, etc. Okay, so this ideal I contains some polynomial, say g1 in x1 alone, and another polynomial in x2 alone, and another polynomial in xn alone. Yeah. So this ideal contains such polynomial if Vi is finite. Now, let us see. So let me. So this G1 x1, G2 x2, Gn xn, they have leading coefficients, and I can make them as monic by simply. The ideal doesn't change if I multiply a polynomial by some non-zero constant. Replace that polynomial by a non-zero constant by the same polynomial, by another polynomial. So the ideal will not change. So without loss of generality, okay, we may assume these are monic polynomials. G1 x1, it looks like x1 d1 plus, say, some lower degree terms. Yeah, lower degree terms. And then G2 x2 looks like x2 d2 and some lower degree terms. and Gn xn looks like xn dn plus some lower degree terms. Yeah, so my ideal contains these such polynomials. Okay. Now look at R mod the ideal. I is the ideal generated by the defining equations f x1 xn over I, and this ring is a complex vector space. S is a C vector space. The polynomial ring R is generated by, as a vector space, it is generated by all monomials in x1 up to xn, and this is a quotient space. So therefore, a generating set of this vector space, a generating set of S as a complex vector space is a monomials, and then they take their residue classes. Yeah, all monomials form a vector space basis of the polynomial ring, but this is a quotient of two vector spaces. So when I take the residue class of monomials, they certainly form a generating set, but these need not be linearly independent. Okay, but since the ideal I contains, let us say, f1 x1, I mean g1, it contains this g1 x1 is x1 d1 lower degree terms. So therefore, when I take the residue class, this residue class in R mod I, it is 0 because gx1 belongs to I. Okay, but this residue class is residue class of x1 d1 plus say a1 x1 d1 minus 1, etc., plus ad1 minus 1. Yeah, but the residue classes add up. So x1, this is 0, this is residue class of 0. So x1 d1 residue class is a linear combination of the residue classes of lower degree polynomials d1 minus j bigger than or equal to 1. So residue class of x1 d1 can be expressed in terms of residue classes of the lower degree monomials. So this we can do for every power of x1 bigger than d1. So therefore, if I take x1 to the power n, where n is bigger than or equal to d1, then this is a C linear combination of residue classes of x1 m, where m is less equal to n minus 1, or d1, yeah, d1 minus 1. And similarly, if I take x1 x2 d2, that is a C linear combination of x2m, where m is strictly less than d2, and so on. So therefore, in this generating set, the generating set consisted of x1 alpha 1, x2 alpha 2, xn alpha n. And whenever alpha 1 exceeds d1, I can replace it by the residue classes of lower powers of x1. Whenever alpha 2 exceeds D2, I can replace it in terms of linear combinations of lower powers of residue class of lower powers of X2. So this is a linear combination. This is a C linear combination of monomials X1, N1, X2, N2, Xn. I should have used M1, M1, Mn, where M1 is less than or equal to D1 minus 1, M2 is less than or equal to D2 minus 1, Mn is less than or equal to Dn minus 1. So therefore, R mod I is finite dimensional complex vector space. So dimension of R mod I as a complex vector space is finite. In fact, it is less than or equal to D1. So this M1 varies over D1 non-negative integers, N2 varies over D2 non-negative integers, and so on. So it's a finite dimensional vector space. So what we approved is that if Vi is finite, implies I contains pure polynomials in X1, Xn's. And then this implies that dimension of R mod I as a complex vector space is finite. Now let me show that it implies that Vi is finite. So suppose my ring is finite dimensional complex vector space. So let R mod I be a finite dimensional vector space, complex vector space. And suppose D is the dimension. Now look at the residue class of 1, residue class of X1, residue class of X1 square, and residue class of X1D. In this vector space, look at these D plus 1 residue classes. What can you say about them? Can anybody tell me?
They are dependent.
They are
Dependent as a vector space
element. D plus 1, so they are linearly dependent. Yeah. So linearly dependent means there is a complex linear combination which produces the zero residue class. So these are linearly dependent. So there exist complex numbers A0, A1, AD, such that A0, 1, A1, X1 plus AD, XD is 0 in R mod I. But the way we add residue classes, this is equal to residue class of A0, A1, X1, A2, X1 square, ADX to the D. That residue class is 0. What does it mean? Residue class of a polynomial is 0 in R mod I means what?
Polynomial is a type.
I.
This polynomial belongs to I. So let us call this polynomial by fx1. So that means fx1 is in I. So similarly, we can prove. Similarly, we can get other polynomials of 2x2 by looking at the powers of residue classes of x2, x2 square, etc. I can get a polynomial x2 in I, and so on. See, so I have proved this part. And if dimension of R mod I is finite, then I contains a polynomial in x1, a polynomial in x2, a polynomial in xn. Now let's show that this implies that Vi is finite. This condition implies that Vi is finite. Vi is finite. Why? Because if a point P is a common solution, okay, if a point P satisfies that f P is 0 for all f in I, then f1 x1 evaluated at P is 0, and fn xn evaluated at P is 0, but this is equal to f1 a1. This is 0, and fn is 0. So a1 has only finitely many possibilities, because a1 is a root of a polynomial in x1, a2 is a root of polynomial in x2, and an is a root of polynomial in xn, and f1 is f1 has some certain degree. So therefore this will say that Vi is finite. Okay, so this is what we have proved. This is the theorem that we have proved for finiteness. And remember, we have used null syntax. The strong null syntax was used to characterize when Vi is finite. So the following are equivalent. Vi is non-empty and finite. Infinite. The second condition is R mod I is a finite dimensional C vector space. The third condition is I contains Amit Kumar should mute himself. Amit Kumar, can you mute yourself?
I am muted, sir, already.
No. There is some noise coming. Munir Nabi, can you mute yourself? Yeah, somehow I have muted myself also. Okay. All right. So I contains polynomials. in x1, polynomial in x2, and polynomial in xn. So this is the criterion for finite algebraic variety. Okay, zero-dimensional algebraic variety. Vi is finite if and only if R mod I is a finite dimensional vector space, and we can test finite dimensionality using special elements in I, that I must contain polynomial in x1, a polynomial in x2, and so on. Are there any questions? Any questions so far about when an algebraic variety is finite, or when a set of polynomial equations has only finitely many solutions? Okay, so that was interesting application of strong null Shinzats. Let us now count. Once we know there are finitely many, how do we count the number of solutions? Okay. So what is the size? What is the cardinality of Vi? Okay. We want to answer this question. So suppose Vi is finite. Suppose Vi has only finitely many points, P1, P2, and Pm. Okay. So there's an exercise for tutorials. Okay. There exist polynomials G1, G2, Gm such that Gi evaluated at Pj equal to 1 if I equal to j, and 0 if I is not equal to j. Does it remind you of something which you have done in numerical analysis? One variable case. I am sure you have studied one variable case. You have some distinct real numbers given, and you want to find polynomials which give you value 1 or value 0. What are these called?
Lagrange interpolation, sir.
Lagrange, Lagrange interpolation point. Lagrange's interpolation polynomials. So for interpolation polynomials, for one variable, one can write exact formula. One can do it for multivariate case also, but there may be many kinds of Lagrange interpolation polynomials. But exercise, if you are given m distinct points, there are m polynomials which satisfy this condition that ith polynomial evaluated at Pj is 1 if I is j, otherwise it is 0. Okay, so grant me existence of these polynomials.
Hello, sir. One more question. The Lagrange interpolation polynomial for one variable is unique actually, like given points actually.
Yeah.
But that need not be unique.
Yeah, for multivariate case, it need not be unique. Yeah, so I am assigning this exercise, construct Lagrange interpolation, some Lagrange interpolation polynomials. Okay. Yeah. So now we want to estimate R mod I. I mean, what is the number of solutions? What is the number of solutions? So suppose I have these distinct solutions. P is P1, P2, Pm. These are the solutions. Okay. Now let me define a map from R mod I to this m-dimensional complex vector space. So elements here are residue classes of polynomials, and I will map this to an m tuple. So calculate f at P1, calculate f at P2, calculate f at Pm. claim phi is a linear transformation? Armada is a complex vector space. It is finite dimensional. Okay, it's a finite dimensional vector space because I am assuming Vi is finite. The variety defined by I is finite. It consists of these m distinct points, P1, P2, Pm. So Armada is a finite dimensional vector space. Cm is a finite dimensional vector space. And the way we add the residue classes of polynomials, okay, it is clear that this map phi is a linear transformation. Yeah. So please verify yourself. Phi is a linear transformation. Now phi is onto. Phi is onto. Can anybody tell me why phi is onto?
By above exercise, it's given n points, n couple points, you can construct polynomial G1, G2.
Say that again.
Taking n tuples of polynomial points actually in CM. So using Lagrange interpolation above exercise, we can construct F
Yeah.
actually.
Yeah, you can get basis vectors in the image.
Yeah.
Using the Lagrange interpolation polynomial. So what is the image of the first Lagrange interpolation polynomial? This is mapped to G1 P1, G1 P2, GM PM. I mean G1, sorry, G1 PM. So this is 1, but these are all 0. So I get the first basis vector from G1. And similarly, the image of the residue class of the second Lagrange interpolation polynomial maps to E2. And then the Lagrange interpolation, the residue class of GM maps to EM. Once the basis vectors are in the image, phi is onto. Yeah. So phi is onto. Let us calculate the null space, the kernel of phi. The kernel of phi is set of all residue classes so that F P1 F Pm is the 0 vector. Yeah. So what can you say about F? What can you say about such an F? F is vanishing at every point of my algebraic variety. You see, F vanishes at every point of my algebraic variety. So Fa is 0 for all A in Vi. What does it mean? Where is F?
The ideal of Vi.
Ideal of Vi. But what is ideal of Vi? It is radical.
Yeah.
It's radical of phi. So therefore, the kernel phi consists of residue classes of F, where F is in radical of phi. And this is the ideal, which is radical of phi mod I inside R mod I. Okay. So therefore we have radical of I over I injects into R mod I, and from R mod I have Cm. Okay, this is a surjective map. So by rank nullity theorem says dimension of R mod I, which is finite, is equal to m plus dimension of radical of I over I. This in particular says, it says that the number of solutions, which is the cardinality of Vi, is less equal to dimension of R mod I. So dimension of R mod I is an upper bound on the number of solutions. And equality, when does equality occur? Equality is true if and only if
I is radical ideal.
I is a radical ideal. Yeah. So if you take variety defined by a radical ideal, then the number of solutions will be precisely the vector space dimension of R mod I. Otherwise, it can be less. Okay, it can be less in general, because what happens, suppose you just have one polynomial in one variable, it can have multiple roots. So the variety could be, the number of roots can be less than the degree of the polynomial. But if you attach multiplicity, then the sum of multiplicities of the roots is precisely the degree of the polynomial. Yeah. So that is why we can get strict inequality if I is not a radical ideal. So tomorrow I will prove a statement exactly by attaching multiplicity to every root, that the dimension of R mod I is the sum of multiplicities of the roots of the simultaneous equations f1 equal to 0, f2 equal to 0, fs equal to 0. That I will discuss tomorrow. But it gives an upper bound on number of solutions. Namely, if I start with a system of polynomial equations, f1 up to fs, take the ideal generated by those polynomials, look at the quotient ring. If the quotient ring is a finite dimensional vector space, then and only then the number of solutions is finite. If the number of solutions is finite, then dimension of this vector space, it gives an upper bound on number of solutions. Now, this dimension can be calculated by symbolic manipulations. It doesn't require any numerical analysis. Yeah. So this is just a remark. I will not explain in this course of lectures. The dimension of R mod I can be determined by symbolic algorithms. Which are based on what are called Grosvenor basis. Okay, I will not discuss this concept, maybe in some other lecture series. Okay, so this is the finiteness theorem. This is called finiteness theorem. Okay, yeah, this theorem is called the finiteness theorem. All right, so there are algorithms to calculate the dimension of R mod I. Those algorithms also tells you whether the given ideal contains a polynomial in x1 alone and a polynomial in x2 alone and polynomial xn alone. These are called Grosvenor basis techniques. One calculates what is called a Grosvenor basis of an ideal in polynomial ring. And by looking at the Grosvenor basis, you can tell whether there are going to be finitely many solutions or not. And you can also calculate the dimension of R mod I as a vector space, as a complex vector space. Okay, these things don't require. So if you are faced with solving a system of polynomial equations which has finitely many solutions, then one has to first calculate an upper bound and then use other methods to actually construct the solutions. In applications, we have to construct the solutions, but exact construction is impossible. Even for polynomial in one variable, we cannot find exact roots in general. We have to be satisfied with approximate roots, and these approximations can be better and better. There are better and better algorithms to calculate approximate roots. But one should know how many roots there are. So for polynomial in one variable, we know that degree of the polynomial is an upper bound. But if you have a system of polynomial equations, then the dimension of R mod the ideal generated by those polynomials is going to be an upper bound on number of solutions. Okay. Yeah, any questions? Any questions so far? All right. So now let us proceed towards construction of solutions. Using eigenvalues. Of matrices. Okay. So what we have done so far is we have used a basic result in algebraic geometry called Hilbert-Null ansatz. Okay. To answer some basic questions. When does a system of polynomial equation have a solution? When does it have finitely many solutions? What is the upper bound on number of solutions? But once we know there are so many solutions of a given system, the next task is actually construct the solutions. Okay. So in order to construct the solutions, we are going to reduce the problem to a problem about computing eigenvalues of matrices. Now that's a very well developed topic. There are many methods of computing eigenvalues of matrices, approximate eigenvalues of matrices, very efficient algorithms. So we convert our nonlinear problem of computing the solutions to a problem about linear algebra for in terms of finding eigenvalues and eigenvectors of matrices. So that's what I want to explain. And the idea is actually lying in polynomial in one variable. Yeah. Any question? Okay. So let's look at one variable case first. Yeah. How to convert the problem of computing roots of one polynomial in one variable in terms of eigenvalues. Yeah. So suppose I have one polynomial fx equal to x to the d plus a1 x to the d minus 1 plus ad, where these ai's are some complex numbers. Right? And d is bigger than or equal to 1. To find roots, I can always assume that it's a monic polynomial. I can divide by the leading coefficient and it is not going to change the roots. So let us take help from what we have observed. We are working in polynomial ring in one variable and then construct this vector space. So take the ideal generated by fx. This is my ring R, and fx has at most d roots. So fx, because by fundamental theorem of algebra, fx has at most d roots. So the variety of the ideal generated by fx is finite. So R is finite dimensional vector space. Dimension of R is finite. It is equal to D. In fact, in this case, it is equal to D. Why? Because you take the residue class of 1, residue class of x, and residue class of xd minus 1. Okay, let us see that this is a basis. This is a basis. Yeah. So now fx residue class of fx is 0, but that is equal to residue class of xd plus ad minus 1, residue class of xd minus 1 plus ad residue class of 1. Okay, so that says that residue class of xd is equal to negative of ad 1, negative of a1, this should be a1, ad minus 1, residue class of x, and so on. So therefore, residue class of any power of xn belongs to the vector space, subspace, the subspace generated by 1 x xd minus 1 for all n bigger than or equal to d. So it's a generating set. These d residue classes generate R mod I, but they are linearly independent. These elements they are linearly independent. So if I take a linear combination of them, which gives me 0, suppose this is 0, this means a0 a1x plus ad minus 1 xd minus 1, this residue class is 0, but that means this polynomial belongs to the ideal generated by fx. What's wrong with that? What is wrong with this? This last statement. Can anybody tell me what is wrong with this? Sakshi?
Yes, since fx has degree d and the degree of fx is d, so the ideal generated by fx will have polynomials of degree d or more. So this is like
Right. So this belongs to this, implies what about the coefficients?
so the coefficients must be 0, all of them.
Exactly. Very good. So this means a0, a1, and ad minus 1 is 0. And that tells me that the residue classes of 1, x, and xd minus 1, they are linearly independent. And therefore, Cx over the ideal generated by fx, a degree d polynomial, this is a vector space, and this is a basis. This is a basis of this vector space. Yeah. So it's a d-dimensional vector space. I know a basis. So you can ask the following question: if my variety is finite, how do I construct a basis of R mod I? So in one variable case, it is easy to construct, but in multivariate case, a basis is given by the techniques of Grobner basis. Okay, so I'm not going to discuss those things. So there are algorithms which generalize this to multivariate situation. Okay, once I have a basis, let us call this vector space by S. Okay, S to S, and so elements of S are residue classes of polynomials in one variable, and I will define a map which is multiplication by x, maps it to x times gx, residue class of x times gx. Okay. this mx is clearly a linear transformation. Mx is a linear transformation. Okay. And a basis of this vector space is 1 x square xd minus 1. Once I have a basis and a linear transformation, I can find matrix. What is the matrix of mx with respect to the ordered basis B? So take mx operating on 1, that is x. Mx operating on second basis vector gives me third basis vector. And mx operating on xd minus 2, this basis vector, gives me the last basis vector. And if I apply mx on the last basis vector, I get the residue class of xd. But the residue class of xd, because my polynomial, remember my polynomial was xd plus a1 xd minus 1 plus a0 d minus 1 plus a0. So the residue class of xd is equal to minus a0 minus, right, a0 times the residue class of 1 minus a1 residue class of x minus ad minus 1 residue class of xd minus 1. So I have expressed the residue class of xd in terms of the basis vectors, and the coefficients of fx are coming here. Okay, so therefore I can write the matrix of the linear transformation, mx with respect to my basis B. Okay, so that matrix, the first basis vector, so columns are representing the basis vectors. It's a d by d matrix because R mod I is d-dimensional vector space. D is the degree of f of x, and 1 is mapped to the residue class of x. So therefore, this is the first column vector. Second column vector is this. Third column vector is this. The last one, see, I get minus a0, minus a1, minus ad, minus 1. So this is, or maybe it's transpose. This is called the companion matrix. Companion matrix of the polynomial fx. Okay, so CF. This is the companion matrix of the polynomial fx. Exercise for tutorial. Determinant or the characteristic polynomial of the companion matrix. Does anybody know what is the characteristic polynomial of the companion matrix?
Yes, sir. It would be a0 plus a1x plus capital A to the power d minus 1 x to the power d minus 1 plus x to the power d.
It is fx.
Yeah, fx. Yeah.
Fx is the characteristic polynomial of the companion matrix of fx. Okay, so therefore the roots of fx are eigenvalues of companion matrix Yeah, so the problem of computing roots of a polynomial in one variable is reduced to computing eigenvalues of the companion matrix. So question, if Vi is finite, can we find a similar result? Yeah. So when you see a result about one variable polynomial, you can ask what is the analog for multivariable, and very often the answers are very interesting and non-trivial. You observe something about polynomials in one variable and ask whether this phenomena occurs in higher multivariate polynomials also. Okay. Now this observation that the roots of f of x are roots of the characteristic polynomial of the companion matrix. This we derived using a special linear transformation. We just looked at this linear transformation mx from S to S. Why restricted to mx? X is after all a polynomial, right? I could have looked at multiplication by any polynomial. Even that will give me, even that is going to give me a linear transformation. Yes. So we look at now multiplication maps by multivariate polynomials on a zero-dimensional ideal. So take R mod I. Now we want to study. We want to now study a similar problem for R mod I when the variety is finite. So let R mod I be a finite dimensional vector space. So R mod I be a d-dimensional C vector space. Okay. So that means there are finitely many solutions. So suppose there are m solutions and the variety of I. Let me list the solutions as points in Cn and take a polynomial in R, say multivariate polynomial, and I can define a linear transformation which is multiplication by G from R mod I to R mod I. And this is the map which sends residue class of a polynomial to the residue class of G times F. This Mg is a linear transformation. This is easy to verify. Mg is a linear transformation. Okay, Mg is a linear transformation. So when I looked at ideal I defined by the principal, it is a principal ideal generated by a polynomial in one variable, and looked at mx, yeah, that was a linear transformation, and its eigenvalues of that linear transformation were precisely the roots of my given polynomial. So similar thing may happen here. Yeah, a similar thing may happen here. So we want to explore that. That can we establish a connection between the solutions and eigenvalues and eigenvectors of Mg. Okay. So I need to charge my iPad just a moment. Okay, can you hear me? Hello?
Yes, sir, you are.
Yeah. So we want to explore this.
I think you need to reshare your screen again.
I have to share the screen again.
Yes.
Yeah, just a minute. Can you see?
Yes, sir.
Okay. Just a minute. I think I lost again.
Yeah, it went back.
Okay. So okay. So I was saying that we observed the companion matrix. Companion matrix. The characteristic polynomial of the companion matrix was the polynomial itself, and therefore roots of fx can be computed from eigenvalues of companion matrix. Now we want to explore similar thing for multivariate situation. Okay, so we want to examine now multiplication by arbitrary polynomial rather than just x. Okay, so take a arbitrary polynomial mg, and suppose my variety is finite. It consists of these m distinct points p1 up to pm. Okay, yeah, and we have interpolation polynomials. So let g1, g2, gm be the Lagrange interpolation polynomials. For these points, which are all the solutions to my system of polynomial equations. Okay. Yeah. So I have these Lagrange interpolation polynomials, and so I can take the residue classes in R mod I. Take the Lagrange interpolation polynomials. There are m of them. Okay, and take the residue classes in R mod I. This is my vector space. Okay, this is my vector space, and now let me state a very important theorem called the first eigenvector theorem. The first eigenvector theorem. So it says that the residue classes of Lagrange interpolation polynomials is a basis of eigenvectors of the linear transformation mg from R mod I to R mod I. Here I must assume that I is its own radical. That is the assumption. Take a variety defined by radical ideal. We know by Null-Schunsatz that every variety is defined by a radical ideal. So I am given some system of polynomial equations, take the ideal generated by those polynomials and then pass to the radical. One can calculate radical of an ideal by purely symbolic methods. Okay, so let's say assume that pass from I to radical of I is a purely symbolic process. So I can just pass to a radical ideal and then take the quotient ring R mod I. Then I know that the number of solutions is precisely the dimension of R mod I. Okay, so I had m points and therefore m is the dimension. Okay, so m is the dimension of R mod I because I is a radical ideal. Okay, we proved using strong Null-Schunsatz that the dimension of R mod I is precisely the number of solutions if and only if I is a radical ideal. So I take now multiplication map by arbitrary polynomial G from R mod I to R mod I. Now this first eigenvector theorem says that the residue classes of the Lagrange interpolation polynomial give me a basis of eigenvectors of Mg. Now, if you know eigenvectors, you can find eigenvalues also, right? Simply operate your Mg on these basis vectors. So you can ask, what are the eigenvalues? So eigenvalues, the eigenvalues of linear transformation is called the spectrum of this linear transformation. Okay, the spectrum of this linear transformation is a set of eigenvalues of this linear transformation is precisely the collection of values of G when you evaluate them at the solutions. Okay. So I'm taking linear transformation induced by G. G has some values at these points. These complex numbers, GP1, GP2, GPM, are precisely the set of eigenvalues of the multiplication operator Mg on R mod I. Okay. I'll explain in a minute why this is useful in computing the solutions, just as one variable case. Yeah, the roots of the polynomial are the eigenvalues of the companion matrix, and this is the generalization of that result. That the eigenvalues, these eigenvalues of any multiplication map Mg are precisely G evaluated at the solutions. You can say we don't know the solution. So what is the use of this? Well, I'll point out what is the use of this. Without knowing the solutions, we can get some information about the solutions. All right, so proof. So first of all, we need to prove that the residue classes of Lagrange interpolation polynomials are eigenvectors of Mg. So we need to show that Mg operating on, say, G1, just as an example, okay, is equal to GP1 times G1. Okay. Now observe that this Gi, the residue class of Gi, is not zero for all I. Only then, only non-zero vectors are eigenvectors. Okay, so we need to first observe that residue class of any Lagrange interpolation is polynomial is non-zero. Can anybody tell me why the residue classes of Lagrange interpolation polynomials are non-zero? What will happen if residue class of Gi is zero? Where will Gi be if residue class of G1 is zero?
In I.
If it is zero, it goes into the ideal. If residue class of any Lagrange interpolation polynomial is zero, that means Gi belongs to the ideal. But ideal is the ideal of variety of I. That means Gi vanishes on every point. But is this true?
GI is 1.
Yeah, this is a contradiction. Therefore, all the residue classes of all Lagrange interpolation polynomials are non-zero vectors in my vector space R mod I. Okay, so they could be eigenvectors. No, zero vector is not an eigenvector. So first, that is the first thing we are checking, that the residue classes of Lagrange interpolation polynomials are non-zero in R mod I. Okay. Now let us show that they are eigenvectors. Residue class of G1 is an eigenvector with eigenvalue GP1, and same thing will be true for residue classes of other GIs. Okay, so look at what does it mean? What does it mean to say that Mg operating on this vector is equal to GP1, which is a complex number, times residue class of G1. This is happening in this quotient ring. This is equality of two residue classes. This is the residue class G times G1. This is GP1, G1. And this is if and only if residue class of GG1 minus GP1, G1 is 0. This is if and only if GG1 minus GP1 times G1 belongs to I. But I is the ideal of variety of I. That means this vanishes at every point. GG1 minus GP1, G1 should vanish at every point. This means GPJ, G1PJ minus GP1, G1PJ should be 0. Yeah. Do you see why it is 0 for every J? If you take J equal to 1, then it says it is just GP1 minus GP1, this is 0. If J is not equal to 1, then why it is 0? Somebody should answer. If J is not equal to 1, why it is 0?
Because G1 PJ will be 0.
G1 PJ is 0 when J is not equal to 1. This is a Lagrange interpolation polynomial. So so we have verified this, that this equation is true. We have verified this equation is true. So therefore, this vector is eigenvector with eigenvalue GP1 and the linear transformation is mg. Same thing is true for the residue class of other Lagrange interpolation polynomials. So what we have proved is that the residue classes of Lagrange interpolation polynomials, okay, these are eigenvectors and eigenvalues are GP1, GPN. These are eigenvalues. What we need to prove is that they are linearly independent. That's what we need to prove now, that they are linearly independent. That G1, GM, okay, this is a basis of eigenvectors of the linear transformation Mg. So wonderful. All these linear transformations are diagonalizable because we have a basis. Once we prove this claim, then any Mg is a diagonalizable linear operator. Or if you write the matrix of Mg, which you can, if I know a basis of R mod I, then you can write a matrix of Mg and assert that that matrix of Mg is a diagonalizable matrix. I have lost once again. Why this is happening? Okay, so let us show that these vectors are linearly independent. Okay, so once again, we know R mod I to Cm. I gave you an isomorphism. That isomorphism maps residue classes of polynomials in R mod I to the vector fp1, fp2, fpn. Okay, and we saw that phi is an isomorphism. Phi is an isomorphism. Okay. Under isomorphism, inverse images of linearly independent vectors are linearly independent. Okay, and I know that phi of the residue class of ith Lagrange interpolation polynomial is the ith basis vector. So therefore, these are linearly independent. Yeah, is this clear? Any questions? Any questions? Okay, so I think I will stop here and next time show you how to construct solutions based on these propositions, the first eigenvector theorem and yeah, Lagrange interpolation polynomials. So I'll prove a theorem called Stickelberger's theorem, which actually arose in number theory, but it has beautiful applications to constructing solutions from eigenvalues of commuting matrices. So next time on R mod I will define certain matrices which are commuting with each other. So commuting matrices which are diagonalizable, they have a common eigenvector. So using common eigenvectors, we will find eigenvalues, and these eigenvalues will give rise to the exact solutions. Okay, but then the problem of computing the solution reduces to computing common eigenvectors of certain commuting matrices. And we can construct these matrices by symbolic manipulations, okay, without knowing the solutions. Okay. All right, so we'll stop here and